So this is a video lesson on the properties of logs and doing log and exponential equations using properties of logs. So first of all, we have some of these more basic properties that we've talked about before. These can be associated back to exponential properties. Again, if you use the fact that when I have a log of base A of x is equal to y, then I also know that if I have a to the y power, that's going to be equal to x. So if I use that logic, I can then go ahead and raise this to both of these to a base of b, so that would make this 1 is equal to b to the 0 power, which we know is true. We also know then that b would be equal to b to the first power, which we know is true. And here, if I raise to the power of b to a base b, then b to the n power is equal to b to the n power. This one's a little more complicated, but think about if you would log both sides, then you would have the log base b of power log of b base m, and that would be the same thing as log base b of m. If I take the log of both sides, these would cancel by one of our power rules we learn later, and then or log of b, then that would just become base b, then that would just become log of b n is equal to log of b n. So those are four properties that we'll use a lot, and they're very fundamental. We also have the log of products, which means if I take the product of two things under a log, then I can take their sum of their two logs separately. Same with the log of quotients, a quotient of two things being taken a log of, and we can write as a difference of two logs separately of those two things. Log of power, if I have n to the n power, I can then go ahead and bring that exponent down as a scalar or a multiple of log b to the n, log of b n. This is also a biconditional, very similar to what we did back in exponents. Remember in exponents, if I had a to the x power is equal to a to the y power, then I can say that x is equal to y. So that's also true with logs. It is a biconditional, so it can go either way. I can add logs or I can take them away as long as the bases are the same. So we'll work on two of the skills in using those properties. One is expanding, the other way is condensing. The expanding formula, if I have a product of two things on the same base, then I can rewrite them as the sum. And remember, if I have a power here, like this squared, that means I can also bring him down and make him something to multiply by. So my real final answer, expanded all the way out, is log base a of x plus 2 times log base a of y. Here in letter B, we'll do the same thing. Log base a of x plus log base a of the square root of x plus 3. Remember, a square root is really just like a 1/2 power. So I can go ahead then in my next step and bring that 1/2 power down out front as something I can multiply by. C and D are both quotients, but maybe D has a little bit of product in there. But if I'm looking at a quotient, I have to remember my top and bottom here of my quotient, so that's my subtraction. Whatever's up top in the numerator, that's what's going to come first in my difference. Quotients and differences are not commutative, so we got to make sure that we separate those two steps in the right order. So then this would also be equal to log base a of x plus 1. Here I have a natural log. So again, go ahead and pause the video if you need to and kind of try it on your own, and then we can kind of look at it together once you've given it a shot. So with the natural log, since I'm trying to expand it, I'm looking at the numerator, and this is my quotient. So if this is my quotient, I'm just going to separate which is going to be the top and the bottom. So I do have a difference in here somewhere. In my numerator, I have an x, so that would be like the natural log of x here, times, so in my expanded version, it's times this. In my expanded version, then that would be a plus. We already said square root is 1/2, so I'm going to bring that 1/2 down, and I have the natural log of x plus 1. Minus is going to be my divider between my numerator and denominator. Whatever's in the denominator is x minus 2 cubed. So I'm going to go ahead and bring that 3 down out front, and I have the natural log of x minus 2. Condensing is very similar, but we're just going to work backwards here. So here I can see that I have a sum of two logs that both have the exact same base, and that's important because if the bases aren't the same, I can't combine them. So my answer here, condensed, would be log base A of 4. However, you saw here that there is a 3 in front of this log, so that 3 can be brought up and as an exponent of what I'm taking the log of. So this would really be x to the third. In letter B, if we break it up into parts, I have 1/2 log of x plus 1 minus, which is important because that minus is going to tell me that I'm going to have the quotient, minus 3 log of x. So let's go ahead and break this up as a quotient. I'm going to have a log base 10, because that's the base of both those logs. And I have a quotient. Whatever comes first is my numerator, so that's going to be a 1/2, which we know is a square root x plus 1, all over 3, which is going to go back up here and be an exponent, x to the third. Go ahead and try C. It's a little more complicated, but it's multiple steps. Be careful with your signs, okay? So we have a plus here, we have a minus here, we have a plus here. So just keep that in mind as you go through that problem on your own. Here I have a 2 natural log of x, that's positive, so that's going to be up in the numerator. I have a natural log of 10, which is a plus, so that's up in the numerator. And I have this plus natural log of 3. Remember, because addition is commutative, I can really pull that natural log of 3 out in front of this 2 times the natural log of x. Because they're all pluses, I can do that, that's fine. But the minus has to be with this natural log right here. So, all 3 of those terms are going to be in my numerator. So I have the natural log of a quotient. The numerator is going to include the x squared that comes right here, because that 2 comes back up, times a 10, and times 3. The denominator is going to include whatever was after the minus sign, so that would be this guy right here, and he would be x squared minus 1 in the denominator. Obviously, we can clean this up a little bit by multiplying 10 and 3 together and putting it as a coefficient of the x squared. Natural log of 30 x squared all over x squared minus 1. Be careful here, whenever I have a log of a sum, okay, make sure that you don't make that a sum of logs. When you break that apart, that's an illegal step, and that's a warning for everybody. When we use our properties of logs, we can't really simplify this too far because of the fact that 3 does not go into 8 evenly. So we can use this thing called the change of base formula, which basically says I can change the base to whatever I want. So if you have an order calculator and you can't do a change of base in your calculator, you might have to resort to log of 8 over the log of 3. Or you can also use a very common log, which is log of base e, or natural log of 8, over the natural log of 3. Either way, when you put that in your calculator, you end up with the same function value for all 3 of these, which is 1.893 rounded in 3 decimal places. So that change of base property is really helpful, especially when a and b are not 1 and n is a positive real number. It'll help you for problems where my base might be a variable. So if you were ever given something where you have log of x 4 is equal to 5, or whatever, you could always use your change of base where maybe this is a different log of 10. That problem is very hard to do with your properties, but if you use your change of base properties, it might be a little more easier to find your solution. Here again, this is just using your calculator, using your change of base formula. So again, I like to use natural log. It's right there on my calculator. It's easy to get to. So if I do that, I can get those function values pretty quickly. Same thing here. Remember, whatever I'm taking the log of, that goes in the numerator, and whatever my bases goes in the denominator. It's kind of like basement, maybe you put it in the bottom because it's lower than the square root of 7. I don't know. However you're going to remember that, make sure you have a little bit of a way to balance that out. Solving equations. So this is our meat and potatoes. This is what we're really trying to get at. These are quite challenging questions because the functions are strange. It does challenge you a little bit. Remember, when you're given these types of problems, you want to check for the individual log domains. So if I'm given the function y equals the log base a of x, I want to make sure that I find the domain of each individual log in the expression, and then make sure that my solutions that I find at the end, make sure that there aren't any extraneous solutions that I might need to get rid of at the end. So remember, the domain of a parent function of log is going to be all the x values that are greater than 0. Or, again, in interval notation, that would kind of be from 0 to infinity. So we'll look at a couple examples together. Feel free to kind of jump ahead and try some problems, but make sure you go back and watch the video to make sure you got all the steps and you found the right solutions. So, whenever you're doing or solving log equations, you have to use the equation that's in front of you. A lot of you want to start simplifying or using your properties of logs to kind of to get to an answer. Remember, you want to go with the problem that's in front of you. So, when I look at this, log base 4 of 8 is just some number, so it's not really, in terms of the domain, a problem. However, log base 4 of x, that's my variable, okay? So that variable x has certain restrictions in terms of what I can put into it. Log base 4 of x, if I just look at it like that, not with the 2, the domain of that function is going to be restricted to the positive real numbers. So here I know that x has to be within the interval 0 to infinity. So when I go through this process to solve, no matter how that process goes, I need to make sure that when I simplify it, that all my answers fit into that domain that would make the original equation true. So when I look at this problem, I have log of 4 on both sides. That 2 right there kind of throws me for a loop. And I can't use my property that, I do have that property of log base a of m is equal to log base a of n. If that's true, if and only if, then n is equal to n. So, if I know that property is true, if I can get both the logs to be alone out in front, then I can go ahead and find my solutions. So, the first thing I'm probably going to do is either use this property, or maybe I know how to simplify something. So I actually want to show you 2 ways that students have done this problem in the past, and both of them give you the same result. Option 1, or way number 1, is kind of getting it back to this form where the logs are on both sides. So the first thing students do is they go ahead and they rewrite this as log base 4 of 8 is equal to log base 4 of x squared. That's the first thing they do. So when they're looking at this function, obviously, they use their power rule to kind of do that. So when you're looking at it right now, there could be 2 solutions, but remember, because we're going from 0 to infinity and it's a one-to-one function, most likely there's only going to be one solution through this process. So now that I have both sides the same, then I can say that 8 is really equal to x squared. And then, again, taking the square root of both sides, that gives me plus or minus the 2 root 2 on the left. And on the right I have x. Remembering, though, that I can't have a negative root 2 over 2 because that would not fit my domain. So my only solution would be 2 root 2. Now that's the way that I would go about it. Other students in the past have said, well, Mr. Ausel, I'm pretty sure log base 4 of 8, I can simplify that. If I use my exponent rules and I kind of work backwards, really, aren't I looking for something where I have 4 to the something power is going to equal 8? And you might be thinking in your head, that should be pretty easy to find. 4 is really just 2 to the 2 power, so 2 to something times something is equal to 2 to the 3rd power, so isn't 2y equal to 3? And then wouldn't that make y equal to 1.5 or 3 halves? So are you telling me that this value is just 3 halves? Yeah, it is. So if log base 4 of 8 is 3 halves, that really simplifies my problem a great deal. However, it gets rid of my log on my left-hand side, which makes it a little more challenging, but still doable. So what you might do next, since you want to isolate the log, is you might divide both sides by 2 to give you 3/4 is equal to log base 4 of x. And then to undo this log, we might have to convert it to exponential form. So I'm going to raise both of these sides to a base of 4, make them powers to a base of 4, and then that's going to cancel this and make this x is equal to 4 raised to the 3/4 power. And you might be looking at me like, Mr. Ausel, those are not the same answers. Well, just doing a little bit of algebra and turning from a fraction exponent to a radical. If I rewrite this as the 4th root of 4 to the 3rd power, and then going ahead and take 4/3, or 4 to the 3rd, and breaking that down into really 2 to the 2 squared is 4 times 3, so that's really to the 6th power. Now I have the 4th root of 2 to the 6th, and I multiply those powers, and then if I take 4 of them out to match my 4 for the radical, isn't this really equal to 2 radical, well, sorry, not 2 radical 2, but it's skipping a step, 2 to the 4th root of, take 2 out, 2 to the 4th root of 2 squared. And if I rewrite that fraction, isn't that really 2 times 2 to the 4 to the 1/2 power? Or, sorry, 2 to the 1/2 power? Because 2/4 is really 1/2. Now I'm pretty sure that's equal to 2 root 2. So again, both these answers are acceptable, and there are 2 different ways to get to the same result. Either way, when I look at these problems, I only have one solution, and it's going to be 2 root 2 or 4 to the 3/4 power. Letter B here, it's really tough to look at this problem because it's natural log. You don't really know, based off the way it's written, if it's the natural log of x plus 1 squared, or am I looking at the natural log of x plus 1, and that whole thing is being squared. Mr. Ausel did a really good job of labeling it out appropriately, because that set of parentheses makes 2 very different functions. And it also affects the domain of those functions. If I jump to my graphing calculator real quick, and I go ahead and I graph those 2 functions, first being the natural log of, we are talking about, the natural log of, in parentheses, x plus 1, x plus 1 squared, and then I also look at the function in red, which will be the natural log of x plus 1, and then that being squared. That gives me 2 very different graphs. Look at the first blue function. And then we look at the red function here. They're very different because if I look at the red function, I have a domain restriction that goes from, on the red function, this is the red function, I have a domain restriction that goes from -1 to infinity. But if I look at the blue function, this isn't a cusp or anything, this is actually a vertical asymptote that's at -1, so that would cause my domain to be from -infinity to -1, and then -1 to infinity. So because of that issue, you kind of have 2 different domains, and it's tough to tell. Let's, for sake of, for what the problem is, let's assume that the squared is only occurring to the x plus 1. That will kind of give you an idea of how it compares to this type of problem in part A. So if it is to the x plus 1, then the domain is going to be from -1 and then -1 to infinity. Meaning that it's going to exist everywhere except at x equals -1. So if that's the case, then let's go ahead and move forward with this problem. Again, lots of ways you can attack it, but I think the more effective way to find all the solutions is to look at this function as it's being raised to the second power, most likely if I'm going to set this equal to 2, there are going to be 2 solutions that I have to find. So let's go ahead and right now, let's go ahead and convert it to exponential form, meaning let's go ahead and raise both these sides to a base of e. And when we do that, we're going to cancel the natural log and e, and we're left with x squared plus 1, x plus 1 squared is equal to e squared. And since I have a squared, I can square root to get rid of those. So x plus 1 is equal to plus or minus the square root of e, or square root of e squared is just going to be e. And then when I subtract 1 from both sides, x is going to be equal to minus 1 plus or minus e. Again, both those solutions are going to be solutions because neither of them are equal to negative 1. A quick way to check to make sure you have all the solution is to pull out your graphing calculator. Since we're going with only the first function where the squared is with the x plus 1 inside, then let's go ahead and just write both sides of the equation into my graphing calculator and look for where they would intersect. Here's again our first function which has a domain from negative infinity to infinity, not including negative 1. And here is our line y equals 2. Obviously I have 2 intersections, and both those intersections are going to go to these values that we found so far. So again, 2 very challenging problems to get us started here with multiple ways of getting to the solutions. But again, you just have to really go back and check your work and make sure that you're following all the properties correctly. Go ahead and try C as well as D. Again, remember your properties of addition. If I'm looking at the sum of 2 different things, then I can probably use my log of sum rules. Remember though, remember, the first thing we have to do is we have to check for our domain restriction. Log base 10 of x plus 1 has a domain that's going to be restricted between negative 1 to infinity. Log base 10 of x minus 2 is going to have a domain that's restricted from 2 to infinity. And when I have 2 different domains, I always want to go with the most restrictive one, because the domain that's most restricted is going to allow for all possible solutions that would fit. Like for example, 0 would fit in this domain, an x value of 0. However, it would not fit in that domain, which would make the entire equation not possible. So this is less restrictive, and this is the domain that I want to go ahead and use because it is the most restrictive domain that I have for this problem. Now that I've looked for my domain, now I can start with my simplifying process. Log base 10, I can then go ahead and take x plus 1 and multiply it with x minus 2. That's equal to 1. Since I only have 1 log, let's go ahead and use the base to kind of raise both sides to a base of 10. That cancels my log and exponent. Gives me x plus 1 times x minus 2, which, we're in an advanced course here. If I have those 2 binomials, I can go ahead and just FOIL those together. And when I do that, I end up with x squared minus x minus 2 equal to 10. Simply subtracting 10 to both sides gives me an x squared minus x minus 12. And then when I factor, I get x minus 4 and I get x plus 3. Again, looking for solutions, the 2 x values that zero product property gives me is a positive 4 and a negative 3. Which means I have to exclude the x equals negative 3 because it does not fit in my domain, which is 2 to infinity. So x equals 4 is my only solution. Letter D here, it's a little different mainly because we now have 2 logs with 2 different bases. One is to a base 2 and one is to a base 4. So I did give you a little hint here, change log base 4 to base 2, but remember, before we jump into that process, we got to make sure that we look for our domains. Here my domain goes from 2 to infinity for the first log. The second log has a domain of 0 to infinity. Which is more restrictive? Well, that would obviously be the 2 to infinity, so that's the one I'm going to use. Again, so it's got a lot of steps, so we got to make sure we use our space wisely and very articulate here with our math. let's go ahead and leave log base 2 of x minus 2 alone, but let's go ahead and change log base 4 to log base 2 using our change of base property. So here I have a log base 2 of x over a log base 2 of 4. You might know that log base 2 of 4 is a scalar value, and if we're trying to figure out what that is, we're going to go ahead and find out, well, 2 to what power is equal to 4? Well, that would be value 2. So let's go ahead and make this a 2 in my denominator. Now, given the problem that we're on, we're going to want to try to get rid of that 1/2, because if I'm going to use that condensing process of using that minus sign and turning it into a quotient, I can't have that 1/2 sitting out in front. So to deal with that, I have two options. I could try to, I don't know, I mean, really, the only option you really have to do is use your power rule, which means if I have a 1/2 multiplied to a log, I can bring that 1/2 up and make that a square root. And now, since I both have logs here, I can use that quotient property, which tells me the log base 2 of x minus 2 over the square root of x is equal to 1. I had a student this year even say, well, Mr. Ausel, you can't have a square root in the denominator. Well, we can for right now. That's okay. And remember, our domain is from 2 to infinity. So if we put a 0 in there, we're all right. Because, that value wouldn't even be part of our domain for us to even plug into. So we're okay for that right now. We could rationalize, but that would just make it more complicated at this point. But maybe later on something will cancel out and drop out of it. Log base 2 of this expression equals 1. So let's get our log that's turned into exponent form, which cancels those two. X minus 2 over the square root of x is equal to 2. Since x can't be 0, we can always multiply both sides by the square root of x, and that gives me x minus 2 is equal to 2 times the square root of x. And I have a first power and I have a half power, so since we have that square root in there, we're going to have to go ahead and square both sides algebraically to get rid of that, or to get everything to an equal degree. This is going to give me x minus 2 squared is equal to x, 4x. It's not an easy problem, but there's some algebra steps we have to go through here. We're going to have to FOIL this expression, and we're going to have to subtract that 4x into my linear terms. So here I have x squared minus 4x plus 4 is equal to 4x, and then when I subtract 4x from both sides, I get x squared minus 8x minus 4 is 0. And if you're looking at this problem right now, you're realizing, oh no, I cannot use factoring for this. I have to do the quadratic formula, or I have to use my completing of the square. Either method will get you to the right values. So we haven't done completing the square in a while. Let's try that method. I'm going to draw an arrow here to kind of show you where my work's going to continue to. So let's go ahead and take x squared minus 8x, leave some space, and set the 4 over here. Divide in half and square it gives me a positive 16. So I'm going to add 16 to both sides. Factoring that gives me a x minus 4 squared is equal to 20. When I square root and add 4, x is going to be equal to 4 plus or minus the square root of 20, which I know is 2 root 5. But right now, let's go ahead and just leave it as the square root of 20. And let's think about those two solutions. They both have to be greater than 2 to fit into my value. Obviously, 4 plus something is going to give me something that's bigger than 2, so I know the positive answer is good. But is 4 minus the square root of 20, is that in my solution set? Well, square root of 20 we can say is obviously greater than 4, but it's also less than, it's less than 5, because the square root of 25 is 5. So obviously this is greater than 4 but less than 5. So when I do 4 minus something that's bigger than 4, it's going to be something that's negative. So I have to make sure I exclude that value from my solution set, meaning that x minus square root of 20 is not part of my solution set, and it only has one solution. That's a challenging problem. But again, a lot of steps, a lot of different things with logs and solving linear equations and quadratics, so make sure you follow each step carefully. These types of problems where we're solving exponential equations using using logs and different things like that, if the bases are equal, then we can use that property that we already know. Because the bases are equal, we can set their exponents equal. But if the bases are not equal, then we have to use what we know about logs. So here, 4 and 10, bases are not equal. I can't take 10 because 4 is not a factor of 10. I can't kind of switch those around and play it around. So I'm going to have to use my properties of logs. It's very easy to kind of isolate your exponent because here it's by itself, and now we're going to convert it into logs. Usually use a common one like log base 10, or maybe even a natural log. Sometimes students like to use the base for whatever the base of the exponent is. Just be very careful about that in terms of putting that in your calculator. It sometimes can give you misleading results. And also log and natural log are right there on your calculator. It's easy to find those values and you can plug those in pretty quickly. So let's go ahead and use the natural log. So here we have the natural log of 4 to the x is equal to the natural log of 10. As long as I do it to both sides, it's okay. Just remember m equals n if and only if the log of the same base m is equal to the log of the same base of n. So let's go ahead then and bring down our exponent. So that means that x times the natural log of 4 is equal to the natural log of 10. Easy at this point, divide by a number. Natural log of 4 is just a number, so we'll divide that to both sides. And my final answer is going to be whatever the natural log of 10 is divided by the natural log of 4. So punching that in your calculator. Natural log of 10 divided by the natural log of 4 is going to give you your value. Rounded to 3 decimal places is 1.661. Same thing with b here. Since my 4 and 27 don't have any common factors that I can simplify to, we're going to have to use our log properties. We want to isolate the exponent here, so we're going to actually add this constant term to both sides to move it away. And with the 4, we're going to go ahead and let's just use the natural log again, and we'll natural log both sides of this equation, and then bring down the exponent. So here now I have a 2x minus 1 times the quantity of the natural log of 4 is equal to the natural log of 27, which both of these are they're just weird, irrational numbers. To solve for x, I'm going to have to distribute and then I'm going to have to go ahead and add and divide. So in this case, x should be equal to whatever the natural log of 27 plus the natural log of 4, all divided by 2 times the natural log of 4. Now you could, if you wanted to, you could condense that, or you could put that exact thing into my calculator to get your result here. So when I'm simplifying that, or I plug that in my calculator, I end up with a value which is equal to 7 plus the natural log of 4 all divided by 2 times the natural log of 4, which ends up being 1.689. So let's look at letter C here. Some of you are saying, well, Mr. Ausel, why aren't we using that one, like 4 and 3? Why don't we use one of their log base 4 and base 3? Maybe that'll kind of cancel a lot of stuff out and make it a little easier. So let's try it. Let's go ahead and use a log base 4, for example. So let's take log base 4 of 4 to the x plus 1 power. And that's equal to log base 4 of 3. It's raised to the 2x minus 1 power. We can go ahead then and bring down the exponents. These cancel. So I have x plus 1 is equal to 2x minus 1 times the quantity of log base 4 of 3. We're still going to have to distribute. So I'm going to have an x plus 1 is equal to a 2 times log of 4, log base 4 of 3x minus a log base 4 of 3. And then I'm going to have to, again, combine like terms. So I'm going to have to add, subtract an x, maybe add this log base 4 of 3. Factor out our x. And with the little space we have the lower notes, we'll divide, so then it makes x equal to 1 plus the log base 4 of 3, all divided by 2 times the log base 4 of 3 minus 1. So when I put that in my calculator, I get an approximate value, which should be around, let's go ahead and plug that in. These are my special logs. So when I put that in my calculator, I get an answer of 3.064. Whew, a lot of steps. Last problem though, and more practice to come obviously. But let's look at this function here with e to the x's. Remember, e is a irrational number that we can use. And we have e to the x minus e to the negative x, all divided by 2 is equal to 3. So again, I want to isolate my exponent. So the first thing I might do is go ahead and multiply both sides by 2. And then here I have a difference of 2 exponential functions. Might be tough to recognize your first step here. So we're going to look at the last one here for letter D. Again, very challenging problem. There's multiple steps. It might take a little bit of imagination to kind of figure out how this all goes. Let's go ahead and first, again, multiply both sides by 2. So that gives me e to the x minus e to the negative x is equal to 6. It might be tough to understand this, but remember, e to the negative x is the same thing as 1 over e to the positive x. And if I have a fraction with something that's not a fraction, I'm going to get a like denominator. To do that, I'm going to have to multiply e to the x by e over x over e to the x. And when I do that, I end up with e to the 2x over e to the x minus 1 over e to the x is equal to 6. So just to kind of get more space, let's go up here. And then once I combine those to get one fraction, I get e to the 2x minus 1 all over e to the x is equal to 6. Multiply both sides by e to the x to get rid of my fraction. So that gives me e to the 2x minus 1 is equal to 6 e to the x. So it doesn't look like we've come very far, but now we have everything, no fractions. We don't have all positive x's. We just got to somehow get those isolated when you get them by themselves. So let's go ahead and bring everything to one side. E to the 2x minus 6 e to the x minus 1 equals 0. If you're following me here, you might see something familiar, something that's unique or familiar about this type of problem right here. It kind of looks like a trinomial, and you're thinking, could I factor that somehow? Well, let's take a step back here. What would happen if I had y squared minus 6y minus 1? Would you be able to factor a problem like that? And you're thinking probably not, because it's not pretty. But if I had it like that, I could use to complete the square. I could use quadratic formula to kind of find the solutions. Well, let's just say in this problem, let's make y equal to e to the x power. It's kind of a substitution method that we'll definitely use in calculus later on. So let's substitute, and let's say, for now, let's make e to the x, let's make it just this y value, right? So if I have y's now, and I'm looking to solve, if I completed the square, I would do y squared minus 6y is equal to 1, and I would probably divide in half and square, which gives me a positive 9, positive 9. Y minus 3 square would be equal to 10, and then I would go ahead and square root. Y minus 3 is equal to the square root of 10 plus or minus. Add 3, y would be equal to 3 plus or minus the square root of 10. But remember, y is not what we're trying to solve for. We're trying to solve for e to the x. So let's go ahead now and just change this y back into my e to the x. Tell you what, that's very interesting. But now I'm not trying to solve for, well, I am trying to solve for e to the x, but now I've isolated just down to 1 e to the x, not 2 of them like I had up here. So, at this point, let's go ahead and natural log both sides so that I can kind of get rid of my e. And x is really equal to the natural log of 3 plus or minus the square root of 10. Always checking to make sure that my solutions fit my set. Looking at that work, can I take the natural log of something that's negative? Because the square root of 10 is greater than the square root of 9, meaning it is greater than 3, I can't have that negative value. So the only answer I can have here is x is equal to the natural log of 3 plus the square root of 10, which in this case would be a decimal approximation at 1.818. There are a lot of homework problems, a lot of challenging problems to try. Check your key with the answer key in the back. You do have 1 through 5 here, so you still have some even numbers to try. But do your very best. 42 is a challenge problem. Make sure you submit that. Good luck, and watch the video again if you need any extra help.